Alright, welcome everyone. In this video we're going to do a 16.9 style problem, but looking at it you may not inherently guess it. Right, so 16.9 is the divergence theorem. In this problem though, we are interested in calculating out the flux. So we have the flux of F, so remember the flux is one of these keywords that you have to remember, one of these definitions. Right, this is F dot n ds. Right, so here is our flux integral here, some surface integral, outward through the surface S, which consists of the sides, but not the bottom, of the pyramid with vertices plus and minus 1, along with 0 in the third coordinate. So, okay, down here, that's the bases. And then 0, 0, 2, so that must be the apex here, the top of the pyramid, as shown below. So again, we're interested in calculating out the flux outward through the surface. So what we want to do, we want to do all of the sides. Let me draw like a little mini picture here. All of the sides, but not the base, not the bottom here. So all of the sides, and then maybe I'll do red or something, or I guess I have orange handy. So not the bottom. So we don't want the bottom of this thing. Which means, sadly, right, we cannot apply the divergence theorem to this. Right? Divergence theorem only works when you have closed surfaces. So divergence theorem would only work if we actually had that bottom. But you can sit here and actually, if you wanted to calculate out the flux kind of each one of these pieces, it would be a huge pain because there's 4 surfaces, right? Each one we would need to get an equation for, we would need to get a normal vector for, we need to do the dot product, all this sort of stuff. So the claim is, using the divergence theorem, we can actually do this faster. So the idea here is that even though this is the one that we want, right here, we're going to go ahead and temporarily say add in the bottom here. So here's maybe the bottom. And that will give us the overall, right, the pyramid with the tops, all of the sides and the base. And this is something that we can use the divergence theorem on. So we're going to go ahead and use the divergence theorem to calculate out this divergence of F dv. And again, this is what we're trying to calculate out. This is our surface integral over all the pieces on the side, but not the bottom. And then this one right here, we can calculate out this by hand. This is only one piece. This is surface integral of the base. So maybe this is some different surface. This isn't the same. Maybe you call it S1 or something like this. F dot n ds1. Or you can call it B for base, or you can do lots of things. So again, the idea here is, instead of calculating out 4 surface integrals, I'm going to calculate out 1 triple integral and 1 surface integral. Then I can go ahead and subtract these, right? And if this is what I'm interested in finding, I can go ahead and subtract this surface integral from my triple integral, and that should give me the result. So this is a clever application of the divergence theorem. So let's go ahead and get started here. Again, the divergence of F, so that's if we had the pyramid with the base included, so all of the sides and the base, this would be the triple integral of the divergence of F. So let's go ahead and look at F, calculate out the divergence. Well, in the first partial derivative, right, in the first component we take the partial derivative with respect to x, I'd get out 1. In the second component, take the partial derivative with respect to y, I'd get out 1. In the third component, we take the partial derivative with respect to z, I'd get out 1. So this is going to be the triple integral of 3. And luckily enough, right, this is a nice pyramid. We know a volume equation for pyramids, right? Volume equation for pyramids go, in fact, let's factor out that 3. Volume equation for pyramids go 1/3 the height times the area of the base of base. There we go. So in this case, well, the 3 and the third perfectly cancel out. The height is going to be this distance right here. Remember, this is the point 0, 0, 2. So it has height 2. So our height is 2 in this case. And then the base. Well, again, we have, this is maybe the points plus and minus 1 in each one of these cases. Let's just kind of take a look at this one right here. We would have, this is 1, -1, 0, And if we were to go over here, this is 1, 1, 0, right? This has length 2. Likewise, this one over here has length 2, right? Kind of when you're flipping this plus to a minus 1, that's switching it by a length of 2. So the area of the base, well, this is, again, a rectangle, or really a square, with side length 2. So 2 times 2 is going to be 4. So the area of the base here, that's going to be 4. So altogether, this is going to be 8. So again, if we were interested in the flux over the entire pyramid, it would just be 8, thanks to the divergence theorem. Because again, we took the divergence, we got 3, and then we went ahead and calculated out the volume of this pyramid, thanks to the volume of the pyramid equation, right? Ooh. But that's not exactly what we want, right? We want the pyramid without the base. So let's go ahead and calculate out the surface integral over the base and figure out how much we're off by. So our surface, our vector field here is still the same. It's x, y, z. And then we need to figure out what is our normal vector. Well, the base, right? This base right here, again, maybe if I just shade this in, we can see that this is a part of the xy plane. The xy plane has the equation z equals 0. So I want a normal vector for z equals 0. Well, I can use, right, we have z equals, so we can use the explicit form for normal vectors. We take a partial derivative with respect to x, I get out 0. Partial derivative with respect to y, I get out 0. Partial, well, I mean, and then our third component is always -1. And remember, we have this plus or minus, right? I have to decide here, should this be facing down or should it be facing up? And remember, in order to apply the divergence theorem, you need outward, right? So these kind of, if I was to throw in the normal vectors here, they would be all pointing outward. So that includes this one right here. We need to be pointing outward. That's away kind of from the origin here. That's going to be pointing downward. So in this case, outward is synonymous with downward, at least for the base here. So we want to make sure that it's pointing downward. So 0, 0, -1 is perfect for us, right? That is outward. So we're going to go ahead and leave that alone. And so let's see, when I go ahead and I calculate this out, this dot product, we're going to have, well, x times 0, y times 0, z times -1. So that's going to be the integral of -z. Okay, but remember, we're on the plane z equals 0. We're about to do a double integral here, which means, right, we would like x's and y's, so we normally get rid of all of our z's. And the way that we get rid of all our z's are remembering where we are, and we're on z equals 0. We're on the xy plane. So this is really adding up 0 a bunch of times. So when you add up 0 a bunch of times, you get out 0. So we have something that we want to know the answer to, right? This is what we're trying to find out. And then we know if we add 0 to it, we get out 8. So what's the thing that we started with? Well, it has to be 8, right? Because 8 plus 0 gives out 8. So our final result here is 8. And so again, the claim here is that this was much faster than evaluating out these 4 surface integrals, using the divergence theorem and then subtracting away how much you're off by. Now, just as an FYI, I would argue that this would potentially not make a great quiz or exam question just because of this 0 right here. I don't like that this is 0. Then if someone used the divergence theorem, they would get the same answer. They would get out 8. They wouldn't realize that there's this extra complication, right? That you're technically adding in a surface and then taking away a surface, right? And so I would hope that, if we were making up an exam question or something like this, that this would be something that is non-zero, hopefully like 1 or 5 or -2 or whatever, just anything non-zero, just so that way you actually get a different answer. Right, and that way you kind of see that, yes, this did matter. You did have to take it into consideration. Otherwise, right, it wouldn't work in general. All right, well, there's an application of the divergence theorem. I hope you guys enjoyed. I'll see you in class, hopefully a couple more times, or at least at the time that I'm recording this. If you're viewing this later, I mean, good luck on the final exam and whatnot. Thanks for watching.